Hello and welcome back to your Chem 4 lecture. In this lecture, we're going to wrap up chapter 6, and a long chapter, I know. We did nomenclature at the beginning, first for ionic compounds, then we did molecular compounds, and then acids. Then in the last lecture, we talked about, in addition to the molecular and acid nomenclature, we talked about Lewis structures, how to draw them. And now what we're going to do in this final lecture, we'll talk about how to interpret those Lewis structures to find out important properties of the molecules that we're discussing. So for example, if we look at methane, methane is CH4, and we drew the Lewis structure in the last lecture. It should look like this. I think it was the first Lewis structure we drew together. Now, when we actually visualize the molecule, it doesn't look like a square, basically, with the hydrogens at four corners. This is more just like an electronic or electric structure. Sorry, it should say electronic. I don't know why I corrected myself there. That's the electronic structure. Now, when these actually arrange themselves, rather than being at the four corners here, they're actually going to get to the corners of a tetrahedron, which is a three-dimensional shape here that we're going to be exploring in lab on Monday. So that's our tetrahedral shape. And then we have the wedge and dash notation we'll talk about here. So that's what we're going to talk about now is how does the Lewis structure tell us about the shape that the molecule takes in? Well, in order to explain that, we need like a theory to be able to understand the connection between the electronic structure and then the geometric structure of the atom itself. And that is valence shell electron pair repulsion theory, or VSEPR theory. What this does is it describes how the electron groups around a central atom arrange themselves. And the idea is basically the electron groups, and I'll define that in a minute, are going to arrange themselves as far apart as possible away from the central atom. Now, let's go ahead and just do a quick definition for you here before we lose it. The electron groups for a particular atom. So this has got to be, you choose one atom, and usually it's the central atom. And the electron groups are the number of bonded atoms plus the number of lone pairs, or as we sometimes call them, non-bonding electrons, or non-bonding pairs, just to be clear. Oh, that goes across the screen. Okay. So, yeah. Now, what is something that electrons have in common, right? Every electron has a -1 charge, right? So when an electron sees another electron, how do they interact? They repel each other because they have similar charges. So the idea here is that any bond that's attached to a central atom is negatively charged. Likewise, any lone pair of electrons is also negatively charged. And so to minimize that repulsion, they're going to get as far away from each other on this central atom as they possibly can. And so VSEPR theory says that the shape of the molecule is going to be determined by the number of atoms and electron groups that are attached to the central atom. Okay, so here's an easy, we're going to kind of build it up from the smallest number of electron groups to the largest that we'll talk about. So from 2 to 4. In your future, perhaps if you go into Chem 1 series in the future, you'll learn about electron groups of 5 and 6 even. And there have been, corner cases where a central atom is bonded to 7, 8, or even 9 atoms at a time. But those are outside the scope of this course. We're going to focus on atoms that are bonded, or I should say have 2, 3, or 4 electron groups. Okay, so starting with 2 electron groups, we can start from CO2. Oops, sorry. There we go. So this was a Lewis structure that we did in the last lecture when we were talking about the double bonds, right? That's how we explained it then. So here, if we were to count up the number of electron groups, that's going to be equal to, again, the number of bonded atoms plus the number of lone pairs. Oops. Sorry, this is always in the way. My little face here. Okay, there we go. Plus the number of lone pairs. Now, again, both of these, you have to remember, this is on the central atom. Don't get confused and think, oh, this oxygen has 2 lone pairs, so it's 2 lone pairs. No, no, no. We're looking at the central atom. That's the carbon. So if I ask you how many lone pairs are on carbon, well, I don't see any lone pairs here. So that would be 0. 0 for the number of lone pairs. Now, how many atoms are bonded to carbon? Well, I've got this oxygen and that oxygen. So that'd be 2. So the total number of electron groups for the carbon here equals 2. We'll have more time to look at this when we're in lab. But I hope I'm kind of laying out what we're looking at here as we say it. Now, you may read in the book, for example, it'll be like the number of bonds. But I think that's a little confusing here because you might say, this is a double bond, this is a double bond. Why isn't that 4? But this double bond, because it's between 2 atoms, always has to have the same orientation. You can't split up a double bond. It always has to be, together. Because think about it this way, these 4 electrons are shared from this carbon to this oxygen. So you couldn't, if you were to try to split those bonds into 2 bonds, you would break the bond. So it wouldn't be a bond anymore. So instead, think of the number of bonded atoms, like I did here. Okay, now how do they orient themselves around the central atom? Well, if we have 2 electron groups, they just get as far apart as they can from each other, which is just on opposite sides of the central atom. And that leads to what we call a linear electron group geometry. Now, I want to point out a couple things here, because this is going to get confusing in a little bit. Note here what we say, this is the electron group geometry. So the electron group geometry this is going to describe the shape of the molecule, the shape, or I should say, no, let's use a better word here. Oops, sorry. Let's go ahead. This is going to describe the electronic structure. In the future, we're going to talk about molecular geometry. So I want to have this as a distinction here for us before we get too deep in. And the molecular geometry only cares about the atoms. Okay, so in other words, the lone pairs don't show up. But we'll talk more about that in a little bit. So in this case, because the 2 electron groups arrange themselves on opposite sides of the central atom, that means that we have a 180-degree bond angle from oxygen to carbon to oxygen. It's just a straight line. That's 180 degrees. Okay, so that's for 2 electron groups. Now, how about formaldehyde? Now, we didn't do formaldehyde. I think it's one of the ones that we'll do in lab on Monday. But formaldehyde has a Lewis structure that looks like this. Oh, let's do it together. This is good practice anyway. Okay, this is good practice anyway. Let's go ahead and do the Lewis structure for formaldehyde together. So the key thing that you need to know is that carbon is the central atom. Okay, so if we were going to draw it, we would put carbon in the middle. It's going to be bonded to 2 hydrogens and 1 oxygen, like that. Okay, so this is our skeleton structure. Now we need to add up our valence electrons. So the number of valence electrons is equal to, we have 2 hydrogens, right? How many valence electrons does hydrogen have? Just the 1, plus 1 times carbon, which has 4 valence electrons, plus 1 times oxygen, which has 6 valence electrons, for a total of 12 valence electrons. Okay, so now we're ready to do our puzzle here, right? So first we draw our sticks, okay, and how many electrons does that use just to draw these single bonds? 2, 4, 6. So that means we have 6 electrons left in our special puzzle. Now, okay, these hydrogens, because they have a single bond, they're full, right? They've got their 2 electrons that they need. So these 6 electrons have to satisfy the octets for oxygen and carbon. So which order do we put these electrons in? Do we put it in the central atom first or the exterior atom, the adjacent atom first? Hopefully you remember, we start with the adjacent atom. So we're going to fill oxygen's octet first. 1, 2, 3, 4, 5, 6. And that uses up all of our electrons. Okay, now is this the final structure? How do we know if it's the final structure? Well, let's look at the octets, right? So we mentioned hydrogen, oxygen, the hydrogens and the oxygen have a full octet now. But what about carbon? I count 2, 4, 6 electrons in its octet. So that's no good. We need to fill carbon's octet as well. So now what do? We don't have any extra electrons to put in here, so we have to make a double bond. So we take this pair here, turn it into a bonding pair, erase these guys, and there's our Lewis structure. It's not very pretty, especially if you compare it to like this one here, but it still gets the job done. Okay, so now our central atom is carbon, and we want to count up the number of electron groups. So remember, that's the number of bonded atoms. So how many atoms are bonded to carbon? 1, 2, 3. And how many lone pairs are on carbon? 0. So 3 plus 0, we have 3 electron groups. Now, in this case, when you have 3 electron groups around a central atom that are all repelling each other, the farthest away they can get from each other is to the corners of an equilateral triangle. So that's kind of why we draw it like this. And what this does is it creates bond angles of 120 degrees. So in other words, if you were to measure the angle here, HCH, that's 120 degrees, HCO, approximately 120 degrees. There's some other factors that come into that, but it's about 120 degrees. Okay, so when we have 3 electron groups, we have what's called a trigonal planar electron group geometry. What else do I want to say? Oh, yeah. So this is just describing the shape here. So linear makes sense, right? It's the 3 are in a line. Trigonal planar also makes sense. I think trigonal is just another word for triagonal. So it's a triangle. Triangular. I think that's what I meant to say. So it's a triangle, and they're all in the same plane. In other words, they share. If you were to draw this on a sheet of paper, they would all, they would fit like that. They share that same plane. And so this is what that actually looks like if you draw it in ball and stick model here. Okay. Next up, let's go ahead and do SO2. Okay. So let's do this one the same way that we did that, because I think that's fun and it's good. The more of these that you see me do, I think the better off we're going to be. So SO2, the sulfur is in the middle. So that's what you need to know, right? I'm always going to tell you, which is the central atom. Usually it's like the one that you have one of is a pretty good bet. Although here for carbon versus oxygen, if it's ever not clear to you which one's in the center, it's usually the less electronegative one. So in this case, carbon versus oxygen, oxygen is more electronegative. So it's not likely to be the central atom. Carbon being less electronegative is more likely to be that. Anyways, I digress. Okay, so we have 1 sulfur. How many valence electrons does sulfur have? And 2 oxygens, which of course have 6 valence electrons again. So that gives us a total of 18 valence electrons to start with. And let's see. So we put in 2 4 electrons here, right, in the bonding group. So make sure that we do that. We take away 4, and that leaves us with 14. So now we have to fill the octets. What gets filled first, the oxygen or the sulfur? Well, remember, we're going to save the central atom for last. So that means we need to fill the octets of the oxygens the adjacent atoms, as I call them, first. So that's 6 for this one, leaving us with 8. So we put 6 over here, and that leaves us with 2. Okay, so sulfur doesn't have a filled octet, right? It still just has 4 electrons total. So we give it a lone pair. Now, are we done? Well, let's check the octets on the central atom. I count 2, 4, 6 electrons on the sulfur. And of course, we know that it needs to have a full octet of 8. So in order to do that, what we're going to have to do is we're going to have to form a double bond. We take this non-bonding pair on this oxygen, and we form a bonding pair right here. Okay, and that's what it looks like. And I know you're asking, why did I choose the left and not the right? You could choose either atom, and you get an equivalent structure. Again, that's a little beyond the scope of this course, but yeah. Okay, so here we go. Now let's go ahead and take a look. Our number of electron groups on the central atom. Again, we're looking at sulfur. How many atoms are bonded to sulfur? 2 oxygens, right? So that's 2 bonded atoms. I'll just put that there. And how many lone pairs are on sulfur? 1. So that's a total of 3. In other words, we know that our EG geometry is going to be trigonal planar. But here's the thing, when we actually visualize the molecule, we have several ways that we can do this. When we actually take a look at it, we can't see the lone pairs. So it doesn't make sense for us to describe the shape of this molecule, including the lone pairs, because they don't show up on when we see the picture of the molecule. So instead, what we do is we want to describe this shape here that we do see. So what we do is we give it a different name for its molecular geometry. And that name is bent. It's bent with a 120-degree bond angle. Because basically, so it's similar to formaldehyde, but instead of this oxygen up here, now we just have a lone pair here that shows up. Again, that does not show up when we actually take a look at the molecule. So this is what's known as bent. So we're kind of filling things out here, but I want to kind of like make sure that we understand. So if we have 2 electron groups, we always have a linear arrangement for our central atom. Basically, by definition, if you have if you only have 2 atoms, so like think about it this way: if you have 2 electron groups where one's a lone pair and one's an atom, that means that your central atom is only bonded to one other atom. So it's technically a linear shape, but any 2 points make a line, right? So it doesn't really tell you much. Here, when we have 3 electron groups that are 3 bonded atoms and 0 lone pairs, that's the trigonal planar molecular geometry. Now, when we have 2 bonded atoms and 1 lone pair on the central atom, again, the electron group geometry stays the same. That's still trigonal planar, but our shape, which I keep calling the molecular geometry, but maybe it's easier just to think shape, is bent, because that's actually what we see when we look at the molecule here. Okay, so hopefully you're kind of getting the pattern. We've done the next 3 Lewis structures already, so we're not going to spend too much time on that. But here we have methane. Methane has 4 bonded atoms to it. So, so the number of electron groups is going to equal 4 plus 0, which equals 4. Now, in order for us to explain the structure of methane, we have to go into 3 dimensions. And this is a shape that we're not always really familiar with. If you play Dungeons and Dragons, this tetrahedron is the shape of a D4 dice. But of course, that probably only applies to me in this classroom anyway. But that's your D4 shape there, and it's a 3-dimensional way of basically having that. In fact, I think I have one around here. Let me pause the video and show you what I mean. Okay, I don't know how well this shows up on video, but I'm going to give it a shot anyway. So what it is basically is it's a 3-dimensional shape. We have 4 triangles kind of all leaning up against each other. Like you might think it looks like a pyramid, but technically a pyramid's where you have a square base with 4 triangles This is just 4 triangles leading up. This is just 4 triangles that are arranged in a 3-dimensional structure like that. We'll play around with those as well on Monday, or just I should say in lab. Yeah, so this is the arrangement. Basically, those get to the corners of the tetrahedron, and so we call this shape tetrahedral. The bond angle for a tetrahedral shape like this is 109 degrees, or approximately 109 degrees. So that's how you can kind of notice that. Okay, now ammonia, that was another Lewis structure we did last time. Here, now all of a sudden, our number of electron groups. We've got 1 lone pair, 3 bonded atoms. So that's 3 bonded atoms plus 1 lone pair. So again, the electron group geometry remains tetrahedral, but the shape is no longer tetrahedral because we don't see the lone pair that's up here at the top of the tetrahedron. So now we say this is trigonal pyramidal. So it's, again, not a tetrahedron anymore. We only see kind of this structure here, kind of all building up on top of it, back here. And this is again, we call this trigonal pyramidal as the geometry for it. And let me know if you're having trouble visualizing this. We're going to see it in lab when we do that. Okay, so finally, that leaves us with water. Of course, we always come back to water. For water, we have our central oxygen here. And the number of electron groups there, we have 2 bonded atoms. That's the 2 hydrogens, 1, 2. And then we have 2 lone pairs on the central atom. So 1, 2. So again, a total of 4, meaning our electron group geometry is still tetrahedral. But now when we look at the molecule, we just see this right here. We can only see this shape here, which again looks bent. So the shape is going to be bent. And just to clarify, this is a different bent shape from our trigonal planar bent shape. So we call that one bent 120. That's all the way back here. Oops, sorry, I went too far. This is bent 120, and this is bent 109. Okay, so here's our big table with all of that information. Now on the test, I am going to provide you with this table. So you're not required to memorize any of this, but you do need to be able to read it. So that's kind of the big challenge here. And again, we'll work together on that in lab. Okay, so let's go ahead and do a sample problem first. Let's use Vesper theory to predict the shape of H2S, which we would know as hydrosulfuric acid, or hydrogen sulfide if it's a gas. So let's go ahead and do our thing. So we've got H2S, and we know that S is the central atom. So what do we need to know? Well, we start from the number of valence electrons. The number of valence electrons, we have 2 hydrogens, so it's 2 times 1, plus 1 sulfur, so that's 1 times 6. So that's a total of 8 valence electrons. Now we draw our skeleton structure here, and we use up 4 of those electrons. So that leaves us with 4 total valence electrons here. Now the hydrogens in this case are happy. They've got their 2 electrons that they need. Sulfur, though, needs its octet, so we can give it 4 more electrons, and then it's got 2, 4, 6, 8 electrons in its octet. That's its happy structure. Okay, next up. So we're going to predict the shape, or the molecular geometry, again, of H2S. So we look at the central atom is the key thing. So the central atom, add up the number of electron groups that it has. How many atoms are bonded to sulfur? 2, right? So there's 2 bonded atoms. And how many lone pairs does sulfur have? 2, right? 2 lone pairs. Okay, so if we have 2 bonded atoms and 2 lone pairs, that means we have 4 total electron groups, which means that we have a tetrahedral electronic structure. So that brings us here. 2 bonded atoms, 2 lone pairs. That gives us a shape of bent 109. So our actual shape here is going to be bent 109. Cool, and that's all you have to do. Okay, So here's our sample exercise, number 18 now. What I'm asking you to do is state the number of electron groups and lone pairs and use the Vesper theory to determine the shape of the following molecules or ions as tetrahedral, trigonal pyramidal, or bent. So just kind of giving you kind of a look there. Now we already did H2S, so that's a pretty bad example. I guess you have to do PF3 and CCl4. Go ahead, pause the video now, try to work it out using your notes. Of course, if you're having trouble, I know this is a very dense topic, so we're going to be working on it later in lab. But for now, give it a try for PF3 and CCl4. Pause the video, and when you come back, we will go through the answers together. So pause. Okay, I'll assume you're back now. So let's go ahead and take a look. So the first thing that you want to do, draw the Lewis structure. For PF3, it looks like this. The phosphorus has a lone pair, and then it's got a single bond to each of the fluorines. And we did H2S. CCl4 looks like this, where the central carbon has bonds to each of the chlorines, and each of the chlorines has a filled octet. So nothing too complicated, right? There's no double bonds or anything here. But, you know, it's a relevant structure that we're looking at. Okay. Now what we're going to do is we add up the electron groups. Well, PF3 has 1, 2, 3 bonded atoms plus a lone pair on the central phosphorus. That's a total of 4 electron groups, which means it's a tetrahedral electronic geometry. It's 1 lone pair plus 1, 2, 3 bonded atoms. That should be a trigonal pyramidal shape. CCl4, on the other hand, has 4 bonded atoms to the central atom. So that can only be a tetrahedral shape. So yeah, trigonal pyramidal, bent for H2S, which we did together, and then tetrahedral for CCl4. Again, make sure to ask questions in the comments down below. I'll get back to you right away. Okay, so moving on. Now, why is it important that we know the shape of a molecule? Well, one of the main driving forces in how molecules interact with each other is whether or not a molecule is polar. This is the difference between oil and water, for example. Oil is nonpolar and water is polar. So because water is polar, those molecules are going to hang out together, and the oil molecules don't want to hang out with the water. They're not compatible. So they separate, and so the chemistry, you know, you're not going to mix oil with water. So that's kind of what we're going to look at here. Okay, so reviewing dipoles. Remember that we have a set of nonpolar molecules. For example, H2, Cl2, and O2. They're nonpolar because they have nonpolar covalent bonds. However, that's not the only kind of nonpolar molecule that there is. You can have a molecule that's nonpolar, even though it has a polar bonds, if all of the dipoles cancel out. Now, let's look at CO2, for example. So remember, CO2 looks like this. Okay, so the way CO2 works is we have 2 different carbon-oxygen bonds, and carbon-oxygen bonds are polar. In other words, if we look at the difference in electronegativity between carbon and oxygen, I think it ends up being 1 point, I should have looked this up before I started talking about it. I think it ends up being 1.1. I'll put that down here, and if I'm wrong, notice it in the comments, and I'll give you 1 extra credit for that. So we have 2 dipoles here. Now, the way that dipoles work is we are going to add those dipoles together to get what we call the net dipole. The net dipole determines if a molecule is polar or not. Okay, so basically what you can do is if you've had a good math class on this, I think one of the calculus classes talks about vector addition. You can just add these 2 arrows together, and if they cancel each other out exactly, so imagine you take this arrow here and then take the exact opposite arrow here, you end up back at 0. That means that you have no net dipole. Now, I know that sounds scary, so don't worry about that if you don't understand any of that vector addition stuff. If instead, we're just talking about, just imagine instead that we're talking about these 2 arrows of the same magnitude kind of pulling each other in opposite directions. Now, if you think of like a tug of war in this case, we have oxygen over here and oxygen over here. So they're equally strong, pulling in opposite directions. When you say go and they start pulling, is the whole thing going to move? Is one of them stronger than the other? No, they're pulled equally in opposite directions. So overall, there's no net dipole. And so that means that CO2 is nonpolar. So the other way that you can think about this is that we have polar bonds that are symmetrically arranged. Now it's pretty easy to see for something like CO2, where you have this in just a linear fashion, or for example, like BF3. BF3 looks like this. If you imagine three people pulling one thing in the middle, they're all equally strong. There's not going to be movement of this thing in the middle. It's much harder to think in 3 dimensions. So I'll just tell you right now, the only 3-dimensional structure that we're going to talk about that has a symmetrical arrangement is the tetrahedron. So if you have each of these 4 corners equally strong dipoles, that means that you have a net nonpolar molecule. Okay. Now, on the other hand, you have polar molecules. We talk about HCl because we have one end of the molecule is more strongly electronegative. So it's going to pull the electrons to its side, and this is not canceled out by any other bond. Okay, water is another good example of this. So water has 2 dipoles. We've got a dipole for each hydrogen-oxygen bond, pointing from the hydrogen to the oxygen. Now, if you want to think of this, again, the real fancy term is vector addition, but all you have to think of is adding these 2 arrows together. If I take this arrow and put it up here, okay, so I take this arrow 1, and then I add arrow 2 to it, do we end up back where we started? No, we ended up all the way up here. So the net dipole is actually, in this case, pointing straight up. So because they add together, they don't cancel each other out. That's why water is a polar molecule. So here we have a net dipole that looks like this. Since it looks a little nicer in the slide, I'm just going to use this as my net dipole. I shouldn't use an arrow, that's confusing. Okay, same thing here for ammonia. Now we have 3 polar bonds, each pointing to the central nitrogen. And we know that that central nitrogen is going to be arranged kind of like this. So those are going to add together and give us a net dipole as well, because they don't cancel out. Okay, so here we go. Let's go ahead and do a little example here. Let's determine whether or not OF2 is polar or not. So what do we need to do? First off, we need the Lewis structure. Then we need to figure out, are the bonds polar? Let's go ahead and draw the Lewis structure first, because I find that to be the most important part. So OF2, let's go ahead and do our valence electron counts. How many valence electrons does OF2 have? Well, we have 1 oxygen, so that's 1 times 6. We have 2 fluorines, so that's 2 times 7. Okay, so total is 14 plus 6, that is 20 valence electrons. Now the structure, I will tell you, oxygen is in the middle. Again, both of our other ways of knowing this, like, okay, oxygen's alone, right? We only have 1 of those, so that's likely to be the center, as well as oxygen is less electronegative than fluorine. So oxygen's in the middle, and we've got 2 fluorines on either side. Okay, so we do this as our skeleton structure. We use 2 4 electrons, so that leaves us with 16 valence electrons to distribute. Start with the outsides and give them octets. So fluorine needs 6 more, and this fluorine needs 6 more. So we just used up 12 electrons, leaving us with 4. Oxygen still doesn't have an octet, so we're going to give it 2, 4 more, and that exactly uses up our electrons. Cool. Okay, so that's our Lewis structure. So to determine if a molecule is polar, start by getting the Lewis structure. Then, once you have the Lewis structure, determine the shape or the molecular geometry. Okay, the shape so the shape plus bond polarity. And those are going to be able to tell us what the net dipole for the molecule looks like. So here we have the Lewis structure for OF2, oxygen difluoride. Now, what is the shape of this molecule? Well, count up your electron groups. We know that we have, for oxygen, 2 bonded atoms and 2 lone pairs. So 4 total electron groups is a tetrahedral electronic geometry. 2 bonded atoms plus 2 lone pairs tells us that we have a bent shape. It's a bent 109 shape. So in other words, if we were to go ahead and draw this molecule, we'd want to draw it something like this. We have O, F, F. And we can put in the lone pairs there if it helps. Okay. All right, so there's our OF2. Great. Now, next thing that we want to do is figure out the bond polarity. So in order to do that, we have to calculate the difference in electronegativity. And the difference in electronegativity is going to be, so for oxygen, it's 3.5, fluorine is 4.0. So we take 4.0 minus 3.5. And that gives us a difference of 0.5. Consulting our table, remember anything above 0.4 is going to be polar covalent. So in other words, this is polar covalent bond. So now we know there's going to be dipoles from between the fluorine and the oxygen. Now fluorine is more electronegative than oxygen, so our dipoles are going to look like this. They're arrows pointing towards the fluorines. Now looking at that, ask yourself, do those dipoles cancel out? No way, right? It's just like water, only kind of in the reverse direction here, where now these 2 arrows add together and give us a net dipole that's going to point down. So we have a net dipole. Is it a polar or nonpolar molecule? A net dipole means that it is indeed polar. There we go. Okay, so that brings us to sample exercise number 19. Is this the last one? Hold on, is this the last one? Oh no, we still got a little ways to go. A couple more things we're going to talk about. So you want to identify each of these molecules as polar or nonpolar. And good news is that these are molecules that we were looking at before are very similar. So you shouldn't have to do too much work on the Lewis structures. But go ahead, remember, the first thing you want to do, Lewis structure. 2, determine the shape. And 3, look for bond polarity. Then you can add these 2 together, and that will give you the net dipole. Okay, so here we go. Go ahead, PBr3, HBr, and CF4. Pause the video here, work these out, and when you come back, we will look at the answers together. So go ahead, pause. Okay, let's give it a shot. So first up, we always want to do the Lewis structure. For PBr3, it looks like this. We have a lone pair on phosphorus, and then the 3 bromines surrounding it. The shape is going to be, well, we have 1 lone pair plus 3 bonded atoms. Check on your chart, that's trigonal pyramidal. And note that that is a non-symmetrical shape. Then we look at the difference in electronegativity. Electronegativity of bromine is 2.8. For phosphorus, it's 2.1. There's a difference of 0.7 there. So we know that it's a polar bond. Do the dipoles cancel out? No, they don't, because it's not symmetrical. Okay, so that means that it's a polar molecule. HBr is pretty easy because there's only 1 bond that you have to worry about here, the hydrogen-bromine bond. So bromine has an electronegativity of 2.8. Hydrogen is 2.1. So the difference in electronegativity is 0.7, meaning that it's a polar covalent bond. And because there's no way for it to cancel out, there's only the 1 bond, it's a polar molecule. Okay, finally, we've got CF4. Oh, wow. Okay, so this is, hold on. So imagine these are F's here. Sorry about that. I got to fix that. Now, in this case, so rather than that, we get F equals 4.0. That's at least easy to do. Now the difference in electronegativity is 1.5. So these are polar covalent bonds. Now the shape itself, though, is tetrahedral. And remember, a tetrahedral shape is perfectly symmetrical. So each of these fluorines has a kind of an opposing dipole in the other three. So overall, the molecule is still nonpolar. There you go. Sorry about that. I messed up the structure. Okay. All right. So that deals with the VSEPR part. Again, we're going to redo this stuff in lab. So if you're feeling a little lost, we have a lot of time to talk about it in lab. Okay. So now we're going to just talk in general about some of the attractive forces in molecules, because they're going to be important to understand how things interact. Okay, so this is kind of how molecules interact with each other is what the focus is here. Starting from ionic bonds. Now, ionic bonds are very strong attractive forces because having a full positive and a full negative charge means that those ions are very strongly attracted to one another. Because of that, most ionic compounds are solids at room temperature, and they form regular repeating crystals. Another example is that sodium chloride, for example, melts at 801 degrees Celsius, which is just an enormous temperature. So in other words, these ionic structures are very stable due to the presence of these ionic bonds. Oops, sorry. Okay, so ionic bonds, extremely strong. Now, what are other types of attractions that molecules can have? And now we're ready to talk about what we call intermolecular forces. So I'm going to use that as a catch-all term here. Sorry, hold on. I'll put this back on. Okay, so these are intermolecular forces. Okay. So polar molecules, when they're put together in a big solution, are naturally going to attract each other, right? Because one molecule has a partially positive end and the other has a partial negative end. And again, positive attracts negative. So the partial negative end of one HCl molecule attracts the partial positive end of the other HCl molecule. And this can go on and on, in a solution or what have you. And these are what are known as dipole-dipole attractions. In other words, the negative end of this dipole is attracted to the positive end of this dipole, and so on and so on. You can imagine this continuing on and going in different directions, right? And then, this carries on down here. It would just go all throughout the sample of the compound that you're looking at. So I want to be clear. Now we're building up forces or attractions that exist between molecules. We've been talking about individual molecules. And now we're ready to see how they add up together. Okay. Now there's a particular type of dipole-dipole force that's called a hydrogen bond. And it's a special type of dipole-dipole force that's about 5 times as strong. So that's why it's important, is because it's very strong. And yeah, very strong for a dipole-dipole force. Now, it's much weaker than an ionic bond, but still, we're talking relative. Now, specifically, a hydrogen bond has to be between a hydrogen atom that's bonded to fluorine, oxygen, or nitrogen, and a lone pair on fluorine, oxygen, or nitrogen. So the most common example of a hydrogen bond is in water. This is something that becomes really important. So note that our dipole here looks like this and like this. And this attraction in particular, it's a type of dipole-dipole force. The hydrogen here that's bonded to an oxygen is then attracted to another oxygen over here, and a lone pair of that oxygen. These hydrogen bonds are the strongest intermolecular force, and this is also what gives DNA its shape. It's what keeps DNA together in the middle of that central helix. So that's why it's important for us to understand what these hydrogen bonds are. And again, it has to specifically be between a hydrogen atom that's bonded to fluorine, oxygen, or nitrogen, and that attraction has to be to another oxygen, fluorine, or nitrogen atom. So those are our, relatively strong intermolecular forces. Number one is hydrogen bonds. Number two is dipole-dipole. Now we have a very weak intermolecular force that we call dispersion forces. Now, dispersion forces are weak attractions that occur between nonpolar molecules. And we don't have to get too deep in the woods here. Basically, what you can imagine is if you have a nucleus here that's surrounded by electrons that are just moving, from time to time, some of those electrons are going to be more on one side than they are on another side. That's going to form what we call a temporary dipole, where this side happens to have fewer electrons, so it's got a partial positive charge. This side happens to have more electrons, it's got a partial negative charge. But that's fleeting. These electrons are going to just, these are going to get right back over here. Now, the thing is, this partial negative charge on this side can interact with another molecule that's nonpolar and push the electrons away, creating a new partial positive charge on that side. These are really weak, but if you have enough electrons floating around, they can actually be big enough to hold molecules together. These are the reason that things like, think like coconut oil. Coconut oil is a very strongly nonpolar compound, but due to the number of carbon-hydrogen bonds that are all nonpolar, these dispersion forces are big enough when they add up that much to hold the whole thing together. Okay, so why do we care about these attractive forces? Well, they determine some of the physical properties that we care about as chemists. The melting points of compounds in particular are directly related to the strength of the attractive forces between the molecules and compounds. If a compound has weak forces like dispersion forces holding it together, usually those melting points are going to be lower. If a compound has very strong attractive forces like hydrogen bonding, then those melting points are going to be much bigger. And then the highest melting points occur in ionic compounds because the attractive forces are so strong because of the full positive and full negative charges holding those compounds together. So just to give you an example, like giving you a range here, magnesium fluoride has a melting point of around 1,248 degrees Celsius. Hydrogen bonding containing compounds like water, of course, the melting point of water is 0 degrees Celsius. Dipole-dipole attractions that exist, for example, in HI. HI is a liquid at room temperature. It melts at negative 51 degrees Celsius. And then finally, dispersion forces, something like difluorine has a melting point of negative 220 degrees Celsius. So yeah, this gives us an idea of the relative strength of forces. So an ionic bond is going to be the strongest force. Then we have our covalent bond just below that. And then much, much farther down the line, we have these weaker intermolecular forces like hydrogen bonding, then dipole-dipole attractions, then dispersion forces. Okay, so that brings us to sample exercise 20. I want you to identify the main type of attractive forces that exist in each of the following compounds: ionic bonds, dipole-dipole, hydrogen bonds, or dispersion forces. Now, together, we're going to do the top one, and then we'll talk about, we'll look through the other ones when you have a break. Okay, so NCl3. In order to figure out NCl3, we need to start by doing its Lewis structure. So the nitrogen is in the middle, surrounded by 3 chlorines. Count up our valence electrons. We have 5 plus 3 times 7. That's 26 total valence electrons. We just used up 6, so that leaves us with 20. We need to give an octet to the surrounding chlorines. So that's 6, oops. There we go. 12, 18, leaving us with 2. That goes on the central nitrogen. Okay, so that's that. Now, the next thing that we need to do is we need to figure out, are these bonds polar or non-polar? So for that, we need the electronegativities of nitrogen and chlorine. And I do not have those numbers. Hold on. Look this up. I'm going to guess. Let me guess first, and then we'll see if I'm right or wrong. So chlorine is 3.0, and nitrogen is, I think, 3.0 as well, now that I'm thinking about it. Click on the electronegativity chart here, and yes, I'm exactly right. So it's 3.0 minus 3.0, put it in, absolute. So that means it is these bonds are nonpolar. Well, we have nonpolar bonds, so we don't have any dipoles. So could we have dipole-dipole forces? Are these ionic? No. Do they have hydrogen bonds? Well, there's not even a hydrogen here, right? So they can't get that. So the only thing that's left is dispersion forces. So for NCl3, it's going to be dispersion forces. So that's how you can do it. Draw the Lewis structure and then evaluate which of those attractive forces exist for it. And then it's on that scale, right? Ionic bonds is the strongest, then hydrogen bonds, then dipole-dipole, then dispersion forces. Okay, now I want to point out something here, which is that your book is a little bit what do I want to say here? Inconsistent with what we've talked about with polar molecules. So based on what I've told you so far, this is a non-polar molecule. Now, the presence of this asymmetry, sometimes people say that this is a polar molecule. So in that case, you would have dipole-dipole forces because you have this lone pair that's negatively charged up here. So you would have a net dipole. I think that's going to be the case for your homework now that I think about it. So let's go ahead and just mention that briefly here. So no polar bonds. Okay, but it's asymmetric. So because it's asymmetric with a lone pair, it automatically gets to be polar. In other words, just think of it this way. This lone pair up here is more negatively charged than these chlorines here. So naturally, there's kind of a net negative charge on the lone pair. So that's why we kind of call that polar, and then that's a dipole-dipole force. Okay, so that's going to come up on the homework, but if you were on the test, for example, to say that this is nonpolar because there's no polar bonds, I would agree with you there as well. Okay, so that brings us to the solutions here. Or go ahead, pause the video now. We're going to look at the solutions when we come back. We've got water, bromine, KCl, and NH3. So let's go ahead and take a look here. So water, of course, it's the classic example of a hydrogen bonding force. Remember water here, it's got a central oxygen that's bonded to two hydrogens. These hydrogens are partially positively charged. Oxygen is partially negatively charged. So there's a net dipole here, and these hydrogens are bonded to oxygen, and they're going to see another oxygen in solution from another water molecule. So that's a partial negative charge, and these are partial positive again. So that's a hydrogen. Now, bromine, Br2, that's just a totally nonpolar bond. The only type of attractive forces that can exist for that are dispersion forces. KCl is an ionic compound, so it has ionic bonds. That's easy enough. Then NH3, ammonia, very similar to water. You've got your central nitrogen with 3 hydrogens. You've got your dipoles as well. And so these partially positive hydrogens are going to see, the nitrogen of another molecule over here that's partially negatively charged. And again, the hydrogen's bonded to a nitrogen, and it's then interacting with another nitrogen. So that's our special hydrogen bond. Okay, that takes us to the end of the chapter. I know this was a big chapter, but we've got a bunch of practice coming up on in lab, both with nomenclature and with this Lewis structure polarity stuff. So we'll make sure to walk through that one more time in lab. And until then, I will see you. And we are done with chapter 6. So you're ready to finish the homework as well. Hopefully that helps too. Ask any questions that you have in the comments below, and I will see you soon. Until then, bye-bye.